On page 624, we're going to do translations. And we've got 3 learning targets here. The first one, we're going to draw translations in a plane and in a coordinate plane. We're going to define translation. And then we're going to write transformations, which in this case will be translations, as functions in the coordinate plane. And that's actually easier than it sounds. So first, what's a translation? Well, we talked about it back in Unit 4, that a translation is a slide. It's a transformation that moves all points of a figure the same distance in the same direction. Translation means moving a figure without rotating, reflecting, resizing, or anything else. Just moving. To translate a figure, every point on the figure must move the same distance in the same direction. Same distance, same direction. All right, let's do one. This is from page 627. It's number 1. It says, copy the figure and the given translation vector. I'll tell you what that is here in just a minute. So, use your straight edge on your paper to make a reasonable copy of triangle BCD. And then draw that little, what appears to be a ray. And I'll tell you what that is in just a second. But get all this drawn. A translation vector can also be called a directed segment. It's not really a ray, because rays go on forever, right? So what this is they're saying that every point in this figure is going to be moved in the exact same direction as this vector and the same distance as it. So it's not a ray that goes on forever. And you can't tell it. It looks like a ray, doesn't it? You have to be told that it's a vector. Okay? It's a directed segment. Directed, so the direction matters. Segment, so it has a beginning and an end. Okay? And it goes in the direction of the arrow. So you start down here and you go there. So look, I copied mine. So make your directed segment something that's easy to copy, like on the edge of your protractor, make it 2 inches or 1.5 inches or something so that you can copy it over and over, okay? Make it some nice, easy measurement to use. And so what we have to do is this. Like in the previous section doing reflections, all our little dotted lines had to be parallel to each other because they were all perpendicular to the line of reflection. All of our vectors have to be parallel to each other because they must be going the exact same direction. Now, this is one thing where I've got it a lot easier than you have, because all I had to do was copy that over and over, and they're all parallel to each other, and they're all the same length. I've got it made, okay? It's a little more effort for you guys. But here's what we're going to do. I'm going to put one translation vector at point C, one at point D, and one at point B. Well, C prime, the point C prime, will be at the end of this translation vector. At least it will be if I can make my pen work. All right, so let's try this again. C prime will be at the end of the translation vector that started at C. D prime will be at the end of the translation vector that started at D. And B prime is at the end of the translation vector that started at B. And then we connect them up. So we use our straight edge or our shape recognition pen, whichever we happen to have handy, to make sure that we get straight edges. And there we go. So that is the translation of triangle BCD into triangle B prime, C prime, D prime using, and I didn't tell you this, but this notation is called vector T. Okay? Like we can call things line T, vector T, that little symbol there with almost an arrow above the T is called, that's the vector symbol. We don't. I'm just letting you know what it's called. Okay? Now, we're not going to do a whole lot of these. We're going to work in the coordinate plane a whole lot more than we're going to do this. But, you know, on a quiz, if I gave you one of those and gave you the triangle and gave you the vector, you could do that, couldn't you? Okay? Now, let's talk about this in a coordinate plane. It says to translate a point along vector, and then look at this notation here. It's not really an ordered pair, all right? It's a little pointy bracket looking thing here. That's the notation for vector, AB. Add A to the x coordinate and add B to the y coordinate. In other words, vector AB, come on. Vector AB means the point, because we move one point at a time, one vertex at a time, moves a distance of A horizontally and a distance of B vertically. In other words, the ordered pair XY becomes X plus A, Y plus B. The X coordinate of the point changes to X plus A. The Y coordinate of the point changes to Y plus B. Now, if A is negative, then the point moves to the left. If A is positive, the point moves to the right. If B is negative, the point moves down. If B is positive, the point moves up. So by using this, so here's the deal. Our book likes this vector notation, but our standard doesn't. Our standard requires us to write it in function notation. Okay? So we need to be able to read and understand both, because our book's going to give it to us as a vector, but our standard requires us to know it as a function. Okay? But what it means is it's giving you directions on how to move the point. It's giving you directions on what direction to move the point and how far to move the point. Okay? So maybe you move it, if X is 3, you move, or if A is 3, you move 3 to the right. And if B is 4, then you would move it 4 up. Or if X is negative 2, you'd move it 2 to the left. And if B is 7, you'd move it 7 up. Get the idea? So that's what the vector notation means. And to write it in function notation, notice that I was able to use the same explanation for both of those. Okay? The vector AB means the point moves a distance of A horizontally and a distance of B vertically. The function notation, the ordered pair XY becomes the ordered pair X plus A, Y plus B, means the point moves a distance of A horizontally and a distance of B vertically. So those are equivalent ideas, just different ways of writing that same idea. Let's see how that plays out. Let's take a look at number 4 on page 627. Use your graph paper. It says graph each figure and its image along the given vector. All right, let's graph the figure. So choose one of your coordinate planes, and we'll graph J, which is 2, 4, 2, 4. K is 1, 1. L is 5, 1. And M is 4, 4. So, oops, I forgot to label M, didn't I? Okay, now we're going to translate it. The translation vector they give us is 7, 1. Now, the first thing we do, because we got to follow our standard, okay? Our standard is to be able to write this translation in function notation. So we need to write the translation using this, okay? Now, what that means then is that each ordered pair, so here's part of my answer, write this down. The function notation for this translation vector is this, that the ordered pair xy becomes the ordered pair x plus 7, y plus 1. That means every point gets moved 7 to the right. When you add 7 to the x coordinate, doesn't that move a point 7 to the right? And 1 up. Because when you add 1 to a y coordinate, it moves up 1 space. Now, applying it to this problem, J prime, its x coordinate will be 2 plus 7, and its y coordinate will be 4 plus 1. What are the coordinates of K prime? 8, 2. Added 7 to the x coordinate, 1 to the y coordinate. So that means L prime must be 12, 2, and M prime must be 11, 5. So now we know we're not using the little dotted, we're not using the actual picture of a vector, but we know what to do. We know how far and in what direction to move each point. Okay? So let's graph these, and at least on my graph, I'm going to have to do a little bit of estimating. I'm going to run out of room, aren't I? And you probably are too, but we'll do our best. All right, so J prime is 9, 5. 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to have to guess where 9 is. 5. There's J prime. K prime is 8, 2. 8, 2. K prime. L prime is 12, 2. So back 9, 10, 11, 12. And then M prime is 11, 5. And mine got bigger. Well, obviously I messed it up a little bit, didn't I? Okay? Since I had to guess, since I ran out of space on my coordinate plane, it shouldn't have gotten bigger, should it? Okay? Let me try that again. Maybe I can undo that. wonder if this will work. Nope, can't do that. There, that's more what it ought to look like. So I was a little off on my M prime and L prime, wasn't I? All right. Questions? You okay with the function notation? You okay with what to do once you have the function notation? All right, number 5. Triangles. I like triangles better, fewer points to move. So we're going to graph triangle DFG. So let's do that. You know, this will fit on here better if I make each space 2 by 2 instead of 1 by 1, won't it? So I think I'll do that. So D is negative 8, 8. So 2, 4, 6, 8, 2, 4, 6, 8. Oops, I went the wrong way. Negative 8, 2, 4, 6, 8. Should be up here. So that's D. F is negative 10, 4. 2, 4, 6, 8, 10, 2, 4. There's F. G is negative 7, 6. 2, 4, 6, 7. 2, 4, 6. Like so. Then we connect it all up with a straight edge. All right, our translation vector is 5, negative 2. Well, if the x coordinate is 5, we'll be moving these 5 to the right. If the y coordinate is negative 2, we'll be moving them 2 up, down. All right, so let's write our function notation. So the ordered pair xy will become the ordered pair x plus 5. Now, I can write y plus negative 2, but y minus 2 is a little nicer, right? And how did I get that? I got it from our vector that the book uses. So let's go ahead. Well, you know what? Do I actually have to write out what all the coordinates are going to be before I do this? I don't have to. Okay? Just start at D and move 5 to the right. So 2, 4, 5, and then 2 down. That's where D prime is going to go. For F, move 5 to the right. 2, 4, 5, and then 2 down. So that's where F prime is going to go. And then for G, 5 to the right. 1, 3, 5, 2 down. It'll go right there. And let's see how close I came this time. Yeah, not bad. Okay. Like with the reflection, we should get congruent figures. Okay. If we've done it right, we get congruent figures. Questions? All right, do this one. Graph parallelogram WXYZ. And then use that translation vector. Does yours look like mine? Are you switching colors and making them pretty like I am? I'm embarrassed I said that. All right. We good? All right, number 23. So I'm all the way over on page 628. Number 23 says to write each translation vector. Well, it depends on which one's the pre-image, doesn't it? Okay, so let's say that the blue one is the pre-image. Isn't that the way the book did it earlier when we were doing dilations, blue first? That's what it seems like. So if the blue one's the pre-image. Now, all we got to do is pick out one point and watch how it gets translated. So if that's point A right there, then that would be A prime right there. So it goes to the right, so the x part of the vector will be positive, then it moves down. So the y part will be negative. So how far to the right does A move to become A prime? 3, 1 space, 2 spaces, 3 spaces, then straight down. So the 3, and then how far down does it go? 1, 2, 3, 4, 5. So negative 5 since it's down. So that's what the book wants. That's the translation vector. But what's our standard going to require us to do? Function notation. So the ordered pair xy becomes, then how do we write the x coordinate? X minus 3, x plus 3, and then y plus 5. Y minus 5. Yeah, that was a little trickeration there. So, on page 627, do number 1, 4 through 6, 15, 17, 19, 23, 24, 35 through 38, and 51 through 54.